Alright, this is going to be what I call X point 2. X point 1 was when we went over integration and the link to Riemann sums. So X point 1 was just review on finding the area underneath curves, where we originally would approximate the area underneath the curve by using Riemann sums, and then we would do the very long way of actually finding the area underneath the curve using limits as n approached to infinity in Riemann sums. And then what we found out was, hey, it's all integration. Integration, wonderful integration, will find us an area underneath the curve over a certain bounded region. So what we're going to do now is extend that, as we kind of discussed today in class, is we're going to be finding the area underneath the curve and bounding that region over a certain interval. And then we're going to be rotating it around a certain axis. So it could be the x-axis or the y-axis. So I'm going to read this to you. Sketch the region bounded by the x-axis and y equals x squared minus 4x plus 5 over the interval 1 to 4. So I have that all down here, but I just have not bound it yet. So I am going to bound this over this interval, or bind it. Bound? Bind? I'm not sure which one it is. Okay, so I'm going to shade that in. This is the area that we would be finding, and once again, we could have used our good old Riemann sums for it and limits as they went towards infinity, or we could have just integrated. Alright, but then it says find the volume of the solid formed by revolving this region over the x-axis. So I'm going to take this area and I'm going to rotate it around my x-axis, and in which case I am going to form a solid. So I do have an image of that solid. Paul's online notes are awesome if you ever have been there before. Okay, so there's kind of a sketch of what I did online. I made up an actual function for it. Okay, and then what happens is when you revolve it around that x-axis, something like this is formed. Okay, and if you can kind of think about slicing these into different pieces, what you could kind of imagine is that you could slice these into what we call those rectangle pieces, and what you have here is a cylinder. Okay, so I'm going to kind of put this cylinder out here. If you just took that one piece, what that was one of our rectangles, and here's where the axes would be. It was one of our rectangles that has been revolved around to form this three-dimensional shape. So here's that lonely rectangle. Okay, and if you can realize what we're doing here is we are creating this disk, which is why we call this first method that we learned today the disk method, because what we're going to use is the idea that the volume of a disk is given by pi r squared. Okay, that's the area of the circle, but then we're going to multiply it by the width of this cylinder or of this disk, or it's also the height if we flipped it on its side, you know, and we had it just laying on the ground like that. So pi r squared times h is typically what we have called it. However, we're going to be looking at r as the height of the rectangle, and that's just going to be our function, so f of c sub I squared times h, which is, you know, just those little teeny tiny intervals that we're separating our area into, so I'm going to call that delta x, and then we have this pi. Okay, so, alright, so once again, here we could have had a bunch of different rectangles, but we're not going to do a bunch of different rectangles. The reason being is because what we have is integration that will make these rectangles infinitely skinny. So we are technically rotating these really teeny tiny skinny disks around that axis. So I just want to bring this up once again. I know I keep bringing up blasts from the past, but this is what we would have used in the past just to calculate the area under the curve. Area under curve. Okay, so we would have just used the height of all of our rectangles times the widths of all of rectangles. And if you bring it back up here, it was the height of all of our rectangles, which would be given by drawing your line or the height up into that curve, which is why we use that f of c sub I, or the function. We plugged our c sub i's into our function. And then all of these little things, all of these widths, were our delta x's. And hopefully our delta x would become something very, very small. Okay, so here we have it, and then eventually what we did was calculate the limit as n approached infinity. And how I got this piece right here, keep in mind that it typically is, when we're looking at c sub I is typically given by delta x times I, and then what I stands for is just the rectangle that you're looking at. Is it rectangle 1? Is it the height of rectangle 2? Is it 3, 4, I equals 5, is it rectangle 5? But delta x then is given by your b minus a over your n. So here, in this case, I had to say 4 minus 1 over our n, and we're letting n be n because eventually we're going to let n equal infinity. But here we would have 3 over n times I, there is our c sub I. And there's our c sub I. And then finally, here's just our delta x. So that was plugging that in. But now what we're going to do is we're going to sum up the disks. So we're going to need this. Okay, and there's that same thing all over again. Here I pulled out my here I pulled out my pi, because pi is just a constant. But oh, this is what we found. Oh, good old integration. We could have just written this from 1 to 4. And then our function, which was x squared plus, minus 4x plus 5. And then we would have just integrated that. Sorry, I ran out of room. We would have just integrated that, so we would have needed our delta x. That was our delta x right here, delta x. So there is our integration. So same thing here. We're going to have pi, and then from 1 to 4. And then this time, though, we're going to need to have our height of those disks squared. So we have x squared minus 4x plus 5 squared, and then there's our dx. Okay, there's our dx. So going back to this, I'm going to have to scroll this down. Alright, so this is what we have. I'm going to be doing, if you were to kind of imagine this is my revolved region, and it is a solid, it's going to form this solid made up of a bunch of teeny tiny disks. Okay, each one of those disks I'm going to want to sum up. So this is where I would use the integration from 1 to 4. Here we're going to want pi r squared, so pi, and then our function x squared minus 4x plus 5, all squared times delta x. Okay. And this one would be kind of a pain in the butt to do. I'm going to just throw that out there. Okay, so this one you could try using the chain rule. Where you identify your u as x squared minus 4x plus 5, and then you would have to say, alright, let's derive this, because you would have to replace that dx, so you would link it together by using the derivative of this, and you're just going to get 2x minus 4, and I would multiply dx to both sides. But then you're going to see this issue of, alright, sure, this is u squared, but then to replace this dx, there is no for example, you can't just say, let's divide both sides by 2x minus 4, because then du is going to be 1 over 2x minus 4, and you have this 2x that you couldn't, let's just write that, you could not pull this out to the front because you have that x there. So once again, you would have to say, alright, then I'd have to replace x again, and you want all x's out of here and replacing them with u. So you can't use the chain rule here. So I'm gonna erase that. So this is kind of a pain, but I'm gonna follow through with this because it's doable. I am gonna pull that pi out because it is a constant, and then only constants can be pulled out. And then I have this to deal with. I can't use the chain rule, and it is a composition function, so I'm going to get rid of the fact that it's a composition function by FOILing. Yes, I know. So if you are really bored, my biggest thing is that you can set up the integration, not so much that you can FOIL things out. But if you know what I'm doing at this point, then stop. But we just need to get it to a point that you can integrate. So I am going to FOIL out. We're going to get x to the fourth. Alright, so I have rewritten this as I'm going to have pi from 1 to 4, x to the fourth minus 8 x to the third plus 26 x to the second minus 40 x plus 25, and all of this dx. And now here's the thing, you can just integrate it term by term because everything is an addition, so I'm going to have pi, and then here's my integration. It's going to be 1/5 x to the fifth, okay, because I added 1 and then I divided by the new exponent, minus, this is going to be raised 1, okay, so it's going to be x to the fourth, but then I'm going to divide by 4, so when you divide 8 by 4 you get your 2, plus, here I'm going to add 1 to my 2, it's going to become 3, so x to the third, but then I'm going to divide by 3. Can I do that? Nope, it's an ugly fraction, so I'm going to just have 3. 26 thirds minus, here I'm going to up my exponent by 1, then divide by 2, so we're going to get 20, and then plus 25x. dx drops out, it's gone because I have integrated at this point, so now, alright, this is even a bigger pain in the butt, you're going to have to put 4 into all of this, okay, and then simplify, and when you do that you're going to get